So in part two of this video series for this example problem, we are asked to start from the energy balance equation and derive an expression that will allow us to ultimately solve for the temperature of the adiabatic flame here. So I've actually gone ahead and started this in part one of this video, and I wrote out this expression here: the total enthalpy in equals the total enthalpy out for this process here. Well, how did I go about getting that expression? Well, since we are saying that this process is at steady state here, we can say that all derivatives involving any changes in internal energy are zero, since there's no changes with time. So here we'll say we have zero on the left-hand side of our expression here, and this will be equal to, well, the enthalpy of what's going in. So the enthalpy of what's going in times dm n, so the enthalpy per unit mass here, and we will subtract from this the enthalpy of what's going out here, so H out times dm out. So since we have 0 here on the left hand side, what we can do is we can go ahead and add over here, and ultimately we will get that the total enthalpy in equals the total enthalpy out. So it's important to remember here that this is the total enthalpy into our stream here and the total enthalpy of what's going out, our product here. So that's what we are asked to do in part two of this video. And in part three of this video, we will need to go ahead and solve for the enthalpies of both our reactants and our product here. And just to give a little bit of a sneak peek, we will see that when solving for the enthalpies, we run into a little bit of an issue, because in order to calculate the enthalpy, we need something known as the heat capacity here, so C. Well, when we have a substance here, let's say any substance, let's say we have air here, and we have its heat capacity, and it's at 298 Kelvin. So we'll say this is C1 here. Well, what happens here with the heat capacity is, if all of a sudden we have air here, and let's say we heat this process up to 3,000 Kelvin, so a big fluctuation in temperature, this heat capacity here will no longer apply, because we are at such a higher temperature. That the heat capacity can change with respect to time. So what we'll see here is we'll actually have a new heat capacity, C2, when we have a process that's let's say at 300 Kelvin instead of 298 Kelvin. So that's what we're going to be doing in part three, and I will show what expressions we will need to derive for that. So that's what we'll be doing next. So let's go ahead and move on to part three of this video series.